So this is Lecture 3, Part 8. Part 8. In this topic, we'll talk about exponential growth and decay problems. Okay, and so what we mean by this is, let me see if I have a math tool for it. Insert math equations. Let's see, does calculus have a, yes, they do. Okay. So with exponential growth and decay, we've got what's called a differential equation. And it's usually the time rate of change of some parameter y, which could be, say, population. And we've got this peculiar looking equation where the derivative of a function y is equal to some constant k times y. All right, so let's fix this a bit. Okay, so consider this. Now, if k is greater than 0, then we have a phenomenon called exponential growth. Exponential growth. And of course, if k is less than 0, then we have a phenomenon called exponential decay. And we'll talk about problems involving various values of k. So this will be exponential decay. Now, let's look at this equation. It's called a differential equation because the left-hand side is a derivative. And the solution to this equation is we want to find a function y which satisfies this equation. Find a function y of t so that when you plug it into this equation, it will be a solution to differential equation. All right, so there's actually several classes, math classes at the upper division level, which treat this subject matter. So I'm not going to go through that content, obviously, in this class. I'll give you the answer, which I think is what everybody wants in this class. Okay, so on page 237 of the Stewart text, the solution is y of t is found to be a constant, which is the function y evaluated at t equals 0 times the exponential function e to the kt power. Okay, and so to show you that this is the solution, what we do is we take this y of t and we plug it in here. We plug it into the differential equation. So y prime of t then is equal to the constant y at 0 is the constant. Okay. Times the derivative of this exponential piece, which is, by the chain rule, the function itself, times the derivative of the exponent, which is just k. And we're taking the derivative with respect to t. Okay? Not x, but t this time. So we have yt, so now we plug this in for dy over dt, and so we have the left-hand side of the differential equation being y naught e to the kt times k, and then the right-hand side of the differential equation is k times y. But y is, if we plug in the value for y of t, it's y0 e to the kt. Okay, so this is a theorem which I give you the solution, the result of, but which you should know. You'll need to know this to solve the problems. And I think you may have encountered this in algebra. Okay, so for instance, we have what's considered population growth. So population growth model. So let me write that down. in population growth, we've got this equation. We have the change. Well, before I write the equation, let me explain what the variables are. Okay. We have this function P of t. This is the population, say, of a city at time t. All right. All right, so now with population growth, we have the differential equation as such. The change in population with respect to time, right? How does a population change with time? In terms of exponential growth, it's written as a constant times the current population. Okay, and if we divide both sides of this equation by population of t, we have 1 over p times the change in population with respect to time is equal to your constant k. And so we define these parameters. This parameter right here, okay, is called the relative growth rate. All right. Okay, and so we may be on occasion asked to solve for this. So solving this differential equation, we have a formula for the population at time t. It's an exponential equation. So the population at time t is given as the initial population. Okay, the population at t equals 0. This is called the initial population. Okay, that's your initial population times the exponential function e to the kt, where k has to be determined from your growth rate. So growth rate is proportional. This is a proportionality. So with this, the interpretation is growth rate is proportional to population size. That's what this equation means. Growth rate is proportional to population size. Okay? All right. Let's see if there's anything else. All right, so I can work an example. There's example 1 is, I'll leave that for you for your review. It's an example of a population growth rate problem. So I'll work, say, number 2 of the exercises in section 3.8. So in number 2, read, a common inhabitant of human intestines is the bacterium Escherichia coli. A cell of this bacterium in a nutrient broth medium divides into 2 cells every 20 minutes. And the initial population of the culture is 60 cells. So in this question, where is my thing here? So in this question, this will be number 2. So section 3.8, number 2, we have the initial population at t equals 0 is equal to 60. So we've got a petri dish phenomena here where the bacterium grow exponentially. All right, and so the question asks, find the, well, part A asks, find the relative growth rate. So in A, find the relative growth rate. Okay, so let's do that. All right, so you recall the formula. The relative growth rate is 1 divided by the initial population times the change in population with respect to t, and that's equal to k. So we need to find k. All right, so now Well, the information we have is, well, we know that the population at any given time t is equal to the initial population times e to the kt. Okay, so what do we have here? So plugging in 60, we have, it's a 6. We have 60, population at time t is equal to 60 times e to the kt, all right? And what other piece of information? Okay, so we know that the medium divides into 2 cells. Okay, a cell divides into 2 cells every 20 minutes. So the interpretation of this would mean that every 20 minutes, or 1/3 of an hour, the population essentially doubles. So if one cell splits every 20 minutes, then essentially the entire population will double in 20 minutes. So one cell splits in 20 minutes, then 2 cells split, you have 1 cell, suppose you have 10 cells at t equals 0. Then in 20 minutes, those 10 cells will double in population because each cell is splitting in 2 every 20 minutes. So basically, at the end of say 20 minutes, the population doubles. So we have 120 is equal to 60 e to the k, and t in this case, if we convert minutes to hours, okay, so 20 minutes is 1/3 of an hour. Okay, so we'll keep the problem in terms of hours, right? So population double in 1/3 of an hour, and so now we are in a position to solve for k. So solving for k, we use the algebraic techniques. We have 2 is equal to e to the k over 3. And then we use the inverse function property of the exponential function, take the natural log of both sides. So we have the natural log of 2 is equal to k over 3. And so we have 3 times the natural log of 2 is equal to k. And then solving, so we have k is equal to, now using the properties of logs, k is equal to the natural log of 8, right? So therefore we have an equation. We have population at time t is equal to 60 times e to the t times k, which is natural log of 8. Okay, now remember the coefficient of the natural log function becomes the exponent of the argument to the natural log function. So this is 60 times e to the natural log of 8 to the t power. And note that exponential and natural log are inverse functions, so a function composed with its inverse is merely the argument, so we have 60 times 8 to the t. So that's the population at time t. So now the question is, let's see, find the relative growth rate. So we have relative growth rate would be, let me see here, relative growth rate is okay, well actually this would be, okay, so this is the answer to part B. If I'm reading in the text, this would be the expression for the number of cells. This is the population in cells after t hours. Okay, so this is actually the B part. So the growth rate the problem sequence got a little bit out of sync here. Population cells after t hours. So this is part B. Let me make sure you follow that. Okay, it's a little bit weird here the way it got jumbled up. Okay, so that's part B. Now, the growth rate then would be 1 over the population at time 0 times the change in the population with respect to t, and that's equal to k. And so we found that k was what? Natural log of 8. So That's your growth rate right there. Okay, so the growth rate is the natural log of 8. So that's the answer to part A. Answer to part A. Looks like a C, doesn't it? Okay, and then so find the number of cells after 8 hours. Well, okay, to do that, you just take your formula. So this will be part C. So population after 8 hours would equal to 60 times 8 to the t evaluated at t equals to 8. Okay, and so you can use your calculator to find what that is. So the rate of growth, what would that be? So that would be the change in population with respect to time. Let me check. Okay, so we have relative growth rate and then the rate of growth. Okay, so the relative growth rate is that. Okay, yeah, so it asks for the rate of growth after 8 hours, so that would be P prime at t equals 8. Okay, and so that would just be, let me check the book here, what the definition of that is. So this is 3.8. I want to be correct here. Don't want to. 3.8. Number 2. I don't recall seeing a definition for that. Yes. Yes, I was correct. So the rate of growth is the change in population with respect to t. And so, okay, so for part D, yeah, the rate of growth, okay, that would be formulated as the change in population with respect to t, which is equal to k. And so, yeah, so it would be this. And so we evaluate t at 8 hours. And so that would be the natural log of 8 times 60 times 8 to the t, where it's evaluated at t equals to 8. So that's your rate of growth. So clearly, that's an explosive rate of growth that's going to consume the entire population. And then the last part is, when does the population reach 20,000 cells? So population, we want to know population t, which is equal to 60 times 8 to the t. And we want to solve for t when p is equal to 20,000. Okay, and so to do that, we just go 8t is equal to 20,000 divided by 60. Then we can take the natural logs of both sides. So we have t times the natural log of 8 is equal to the natural log of 20,000 minus the natural log of 60. Okay, and then solving for t. T is equal to the natural log of 20,000 minus the natural log of 60, whatever this number turns out to be, divided by the natural log of 8. So whatever time that is. So many hours into the future. Okay. All right, so that's number 2. So the next class of problems now regard when we have k less than 0. And this would be exponential decay. And so the classic example of an exponential decay problem would be radioactive decay. So Okay. So it's the same formula, except k will be less than 0. So if m of t is the mass remaining from an initial mass m sub 0 of the substance of a substance after time t, then the relative decay rate is what? We have a formula. It's defined as this formula, so I'll write it here. It would be, okay, minus 1 over m times the change in mass with respect to time. It, of course, must equal to a constant. Okay, so very similar as population growth, but this is quantity, this is radioactive decay. So solving this differential equation using the theorem, we have the mass at time t is equal to the initial mass times e to the kt. Okay, and k is less than 0 in this case. So then we have what's called the half-life. So the half-life, and you may have had this in algebra, half-life is the time required for half of any given quantity to decay. Okay, so you start off with 1 kilogram. How long will it take you to reach a half a kilogram? Okay, so let's do an example, say number 10, section 3.8, number 10. So a sample of tritium-3, okay, so a sample of tritium-3 decayed to 94.5% of its original amount after a year. So what is the half-life of tritium-3? All right, so 94.5% after 1 year is remaining. Okay, so, all right, so we can look at it from this way. So we're going to have daily decay, okay? So if, I should be careful. This is number 10, section 3.8. All right, so part A. We're asked to calculate the half-life of tritium-3. So let y of t equal to the mass after t days. Okay. So you start off with, does it tell you how much you start off with? Just a sample, some given mass. So mass after t days. Okay, we don't know how much mass we have, but after t days we've got this, all right? And so we parameterize the initial mass. Say let that equal to a kilograms or grams or whatever. And we use the differential equation, the solution to the differential equation, to note that the mass after t days is equal to your initial mass times e to the kt for exponential decay. Okay. All right. So now, so in terms of years, okay, the amount after 1 year is equal to a e to the k. So in terms of years. So if we let t be in terms of years, after 1 year we have this amount. And so we can solve for e to the k. So, well, okay, what can we do here? So after 1 year we have 0.945 of the initial amount. Okay, so that would be 94.5% of the initial amount. Okay, after 1 year. So then we can solve for e to the k because now the a's will cancel in this equation. See how the a's cancel? A was your initial amount, but we really don't need to know it. We just need to solve for the exponential decay factor. And so we have e to the k Oops, wrong pen. E to the k is equal to 0.945. And so taking the natural logs of both sides, then k is equal to the natural log of 0.945. Okay, and so that answers the question, what is that? Okay, so we need to know the half-life. All right, so the half-life, yeah. So what is the half-life? So we have, then we have y of t is now equal to a times e to the natural log, your k, this is your k value, 0.945. Okay, there's your, and that has to equal to 1/2 a. So we need to solve for t so that the amount is equal to half the original amount. All right, so in solving, okay, so again, the a's cancel, and we need to figure out t. Okay, so when does y of t equal to 1/2 the original amount? Okay, and so in solving for t, we can go ahead and take the natural logs of both sides. So we have the natural log of, well, actually, yeah, the natural log of 1/2 is equal to, let's see here, yeah, the natural log of e to the natural log of 0.945t, okay? And then we have the natural log of 1/2 is equal to the natural log of, let's see, what do we have here? The natural log of, oops, sorry. Let me see how we can fix this. That would be the natural log of what? E to the natural log of 0.945 times e to the t, because I can take my e and I can distribute it term by term in the product, which is in the exponent, okay? And so this would be equal to the natural log, oops, not natural log. Yes, natural log, that's correct, natural log. So these are inverse functions, so this would be the natural log of 0.945, I can never write what I say, times e to the t, and we know that the natural log of a product is let's see here. Is that right? Oh, wait a minute. I think I made a mistake here. I see. KT. Something is not right here. Let me check here. I think I may have made a mistake. E to the natural log. So, yes, 9.45 e to the t. Hang on. I think there's a mistake in the book. All right. Yeah, this should be okay. E to the, no, wait. E to the, yeah, there's a mistake here. So we have this. All right. Let's see. I think there's a couple of mistakes here. So this equation is okay. Let's see here. the natural log of E. Okay, so that's the exponent. Okay, yes, that's the exponent. So now we use the inverse function. So we have, oh yeah, okay, so now I see how, I see what's going on now. All right, so then this becomes, so yeah, I see. Yeah, I forgot the exponent, lost track of the exponent. The exponent is, to the exponential function, this is the exponent, this product right here. And so the natural log of e to something is something. Okay, so we have the natural log of 1/2 is equal to the natural log of 0.945 times t. Okay, and then we can divide both sides by the numbers. So we have the natural log of 1/2 divided by the natural log of 0.945 is equal to t, which, if you solve on your calculators, will be 12.25 years. Okay, so that's a pretty stable substance. All right. Okay, so that's the half-life. Make sure it's right. Okay, so we solve for k, then we have a function for y of t. We want to find where y of t is equal to 1/2. It's the time at which the initial mass is 1/2. The time for which it takes the initial mass to decay to 1/2 of the initial mass. And so we have, yeah, so taking the natural logs of both sides, the natural log, yeah, that'll work. Take the natural logs of both sides. Okay. All right, and then, so we have, that was part A. Part B is, how long will it take the sample to decay to 20% of its original amount? Okay, so in this case, solve just like with half-life. The formula for mass at time t, so mass at time t is equal to the initial amount times e to the k, which is the natural log of 0.945 t. Okay, and we want to know at what time the initial amount becomes 20%. What time does the mass reach 20% of its initial mass, like this? So we need to solve for t in this equation. So again, as before, the a's will cancel. We never needed to have knowledge of a. And so taking the natural logs of both sides again, so we have the natural log of e to the natural log of 0.945 t is equal to the natural log of 0.2. Okay, and then so the natural log of e to something is something, so we have the natural log of 0.945 times t. Okay, I keep thinking the t is in the natural log, but it's not. It's actually this. Is equal to the natural log of 0.2, and then solving for t, just do the division. We have t is equal to the natural log of 0.2 divided by the natural log of 0.945, and solving, that's 28.45 years. Okay. So in 28.45 years, your mass will be 20% of its original mass. Okay, so exponential decay. So the next class of problems we'll be talking about will be called Newton's law of cooling. And this is a rather interesting problem. Okay. In Newton's law of cooling, states that the rate of cooling of an object is proportional to the temperature difference. Oops, let me spell proportional. Okay, so the rate of cooling is proportional to the temperature difference between the object and its surroundings. Provided the temperature difference isn't too large. Okay, so Newton's law of cooling. So in Newton's law of cooling, the equations are stood up like this. We have big case, uppercase T of T. Okay, so that would be the temperature of an object at time T. Okay, and then T subscript S, that's the temperature of the surroundings. Right, and then we have the differential equation, which is not the same. So we'll pose a different kind of challenge here. So the differential equation will be written like this. So we have the change in temperature with respect to time is equal to your cooling constant times the temperature at the given time minus the temperature of the ambient surrounding. Okay, so this is Newton's law. That's the formula that we'll be dealing with. I forgot to close paren, so we need to close like that. All right, so there's Newton's law of cooling. All right, so let's do an example. Now the problem with this differential equation is that it is not the same as the one we've been working with up to this point. The one we've been working with has been, say, well, the change in y with respect to t is equal to ky. Okay? There was no subtraction going on. Now we have a subtraction. So the strategy for solving Newton's law of cooling problems is we have to transform this equation, Newton's law of cooling equation, into a format like this. Okay, so we're going to have to parameterize the subtraction in terms of a single variable. So let me do that by example. So this would be, say, question number 14 in the text, section 3.8. All right, ooh, it's somewhat gruesome here. Is that 14? Maybe it's not 14. It must be 14 from the. Okay, so maybe this one is not in the book. This is in an older book. I'm sorry. Let me see if it's in this book. I don't think it's in this book. Not 14. So this will not be question 14 in the Stewart book. It's actually question 14 from an older version of Stewart's book. So I'll write it out for you. I'm looking and I'm not seeing it here. Okay, so he didn't read it. Okay. Well, anyway, I'll go ahead and write it for you. So from a previous edition, we have a thermometer is taken from a room where the temperature is 20 degrees centigrade. 20 degrees C. Okay. So the thermometer is taken from a room where the temperature is 20 degrees centigrade to the outdoors, right? Where the temperature is 5 degrees C. Okay. So after 1 minute, the temperature, or the thermometer, the thermometer reads 12 degrees centigrade. All right. All right. So the question, the first part of the question asks, part A, what will the reading on the thermometer be after 1 minute? Okay, can you see what physically is going on here? You take a thermometer from a warm environment to a cooler environment, and then after 1 minute, what will the reading of the thermometer be? Okay, so we have to use Newton's law of cooling to solve this question, this problem. So using the formula, we have change in temperature with respect to time is equal to K, your cooling constant, times the temperature, the initial, the temperature at time t, okay, whatever time it is, minus the surrounding temperature. So this would be 5 degrees. So we'll take Ts to be the outside temperature, because the thermometer is going to be sitting outside for a number of minutes, and you want to know what the temperature, or how long it will take for the thermometer to register 12 degrees when the thermometer is sitting in an environment where the ambient air temperature is 5 degrees. So the solution proceeds as follows. We define this function y of t to be equal to the temperature at time t that the thermometer is registering minus 5. Okay, in other words, this thing right here. Okay, so now the change in y with respect to t is equal to the change in t with respect to t. Okay, and remember, the derivative of a constant with respect to time is just 0. Okay, so now we make the substitutions, and we have we make the substitution so that the equation is recast in terms of y. So now we have the change in y with respect to t, which is the same as the change in t with respect to time. Okay, that's equal to the constant times y of t, because we parameterized t minus 5 to be y of t. We did that, okay, so that now this should look familiar. This is the standard form of the exponential growth and decay equation for which we have a solution, because we know from the opening of this lecture that y of t, which is the solution to this differential equation, is equal to the initial value for y. In other words, y at t equals 0, okay, times e to the kt. All right, and so what is y of 0? Okay, so we need to know what this value is, this coefficient in the function. Well, we have y of t, we use this equation right here. Use this equation. So y of t is equal to the temperature at t minus 5. And we just plug in t equals 0, so we have y of 0 is equal to t of 0 minus 5. Now t of 0 is the initial temperature. T of 0 occurred inside. So we were given that t of 0 is the initial temperature of the thermometer, which was read to be 20 degrees, the indoor temperature. So that means y of 0 is equal to 15. Okay, so now we have the equation y of t is equal to 15 e to the kt. Okay, and so now we have an expression for, so we take this y of t and we plug it in here, and we solve for t of t. Okay, so once we make that substitution, we have the temperature at time t is equal to y of t which is 15e to the kt, okay, plus 5. So there's your equation for temperature with respect to time. So now, so let's see. What will the reading on the thermometer be after 1 minute? So after one, okay, not 1 minute, but 1 minute more. So after 2 minutes was the question. After 1 minute, the reading is 12, right? After 1 minute, it's 12. So what will the reading of the thermometer be after 2 minutes? Okay, now, yeah, so we have to look at that data. So after 1 minute, okay, the temperature will be, of the thermometer will read e to the 15 times e to the k, t is equal to 1 plus 5. And that is equal to 12. Okay, and so we have e to the k is equal to what? Solving, that would be 7/15, right? And so taking the natural logs of both sides, we have k is equal to the natural log of 7/15. Okay, so now we have a fully fledged formula for temperature at T, okay, in terms of time. So that would be 15 e to the natural log of 7/15 times T, okay, plus 5. Okay, and we can simplify this. Okay, so the coefficient T becomes the exponent, so that would be 15 times e to the natural log of 7/15 to the T power plus 5. And now, and knowing that e and natural log are inverse functions, we have the formula temperature with respect to time is equal to 15 times 7/15 to the T power plus 5. And the question asks, what is the temperature after 2 minutes? So T of 2, just plug in 2. And you'll need your calculator to answer this question. So that would be 15 times 7/15 squared plus 5. And so I got 8.3 degrees centigrade. Okay, so after 2 minutes. And then the next question is, when will the thermometer read 6 degrees? Okay, so at what time does the temperature equal to 6? All right, so we use our formula again that we derived. And so for part B, the temperature will reach 6 at what time? So after how many minutes? So 6 is equal to 7/15 times 7/15 to the T power plus 5. Okay, now we need to solve for T, so we have 1/15 is equal to 7/15 to the T power. And then take the natural log of both sides. So we have the natural log of 1/15 is equal to T times the natural log of 7/15. And then dividing both sides by the natural log of 7/15, we have T is equal to the natural log of 1/15 divided by the natural log of 7/15. Okay, and I get, that's approximately 3.6 minutes. Okay. Okay, sorry about that. I had to step away for a second. Okay, so that's an example of Newton's law of cooling. What's the next category? So there's one more category of problems in this section, and that's called continuously compounded interest. Okay, so the finance section. So we'll move off of physics and we'll get into finance. And so we have continuously compounded interest. So if an amount A sub 0 is invested at an interest rate R, then after T years, it's worth this. Okay, so let me write the equation using equation editor. Amount is equal to the initial amount times 1 plus the interest rate raised to the power of T. Okay, so this is the amount after, so your initial investment amount and then the return after T years at a given rate is this. Okay, so now, what's going on here? So usually, however, interest is compounded more frequently, say n times a year. Then in each compounding period, the interest rate is R divided by N. And there are NT compounding periods, NT years. So the value of the investment is okay, and so the formula for that would be A is equal to the initial amount times what? 1 plus the ratio of your rate divided by the number of compounding periods. All of this raised to the NT power. All right, so if you have n compounding periods. Okay. So now, of course, what we usually like to do is we like to let n run to infinity. So most financial institutions do that these days. So if we let n go to infinity, then we'll be compounding interest continuously. Then we have continuously compounded interest. Okay. So the formula then becomes this. So we have this. So we have A of t, the amount in the account at any given time t, would equal to, let's see here, maybe, yeah, would equal to the limit as n approaches infinity of the initial amount times 1 plus r over n to the nt. Okay, and so how do we solve this? Okay, so, and I think we may have solved a similar problem a couple of lectures ago. So let's simplify this limit. Okay, the way the trick is to factor the exponent in this expression as follows, so that we can use a limit law. So we raise 1 plus r over n to the n over r power, okay? And then we raise the quantity in brackets to the RT, because we know we multiply the exponents in this expression. So if we multiply the exponents, we get that back. All right, and so we can recognize then, oh yeah, and then by the limit laws, we can bring the limit operator inside the brackets. So because A naught is just a constant, we can factor the constant out. So we have this. Okay, so the constant goes out, and then the limit operator comes inside the brackets because we're taking the limit of a continuous function, and n is growing large, so we can remember our recent discussion on limit laws. The limit of a function raised to a power is the same as the limit of the function raised to the power. So that's what's going on here. Okay, so we can do this. Okay, and then that is to the RT power. Okay, and then so we make a variable substitution. So we say let m equal to n over r. Okay, so we'll make a change of variable substitution in the limit operator. So as n goes to infinity, so goes m. Okay, so n and m both go to infinity because they're only related by 1 over r. Okay, and so now after transforming the problem, the transform problem then becomes A of t is equal to the initial amount times the limit as m approaches infinity of 1 plus, now r over n is 1 over m, and that would be raised to the m power, and all of that to the RT power. Okay. And so we recognize the quantity in brackets as being E. So we have, for continuously compounded interest, the formula. And so this formula you may have used in algebra, that you never knew where it came from. And so it came from a judicious use of the limit laws and through variable manipulation. So let's see, can we do a problem here? Let's see. Okay, yeah, so this will be question number 20 in section 3.8. This one is in the text. So in question 20, I'll do it on the next page. I'll write it here. How long will it take an investment to double? Oh, sorry, I should write. This is number 20, section 3.8. Okay, so how long will it take an investment to double in value if the interest rate is 6%, oh, you wish, right? Compound it continuously. Okay, And so the answer to that question would be as follows. Since we have continuously compounded interest, we have the formula A of t is equal to A of 0 times e to the RT. Okay, but your amount is twice your initial amount. So what we have is we have A of t is equal to 2 times your initial amount. And we want to find how long it takes to get to 2 times your initial amount. So twice your initial amount is equal to your initial amount times E, and then our interest rate is 6%, right? And then T. So we need to solve for T. So the initial amounts cancel. And then we just use we take the natural log of both sides. So then we have the natural log of 2 is equal to 0.06t, 0.06t. And dividing by t, 0.06, we have natural log of 2 divided by 0.06 is equal to t, which is equal to 11.55 years. Which I'll write as YRS, years, okay? And then, okay, so now we have this quantity called the equivalent annual interest rate. So let me introduce that. So equivalent annual interest rate is essentially what the interest rate is if it were compounded, if the interest rate were compounded once a year, right? Instead of continuously, suppose the interest rate were compounded continuously, and we want to find this particular rate. So the way you calculate that is the equivalent annual interest rate would be found using this formula. So we have the amount after 1 year is equal to the initial amount times 1 plus r to the t power. Okay? And that would equal to essentially your continuously compounded interest rate. Okay? So, and these are evaluated at t equals 1 for 1 year, right? So, use the compounding interest rate formula for 1 compounding period. So n is equal to 1, okay, and set that equal to your continuously compounded interest rate. So you can find your effective annual interest rate, or the equivalent annual interest rate, the annual interest rate. All right, so we can go ahead and solve. So 1 plus r to the t, okay, is equal to e to the 0.06t, okay? And since t is 1 for 1 year, we have 1 plus r is equal to e to the 0.06. Okay, and so r is equal to e to the 0.06 minus 1, which is 6.18%. So if you had just 1 compounding period, okay, if interest were compounded annually, that is, if interest were compounded annually, instead of continuously, in order to make the same amount for 1 compounding period, for interest rate compounding annually, you would have to make 6.18%. So you'd have to earn a higher interest rate for n equals 1 than if n were infinity, basically, is the interpretation of that. All right, so that is it for section 3.8. Okay, so the next topic will be a treatment of related rates, and so this is where we deal with quite a few different kinds of word problems. So this is a little bit of a challenging section. So I'm going to end it right here for section 3.8, and I'll start another video for section 3.9.